Okay, so now we'll take a look at electric energy. So let's say we have two charges, Q1 and Q2. Okay, we don't care about the mass of the charges or anything else when we're talking about the electric energy. Because electric potential energy, if R is the distance between them, this is just a constant K times Q1, Q2 over R. So we see this is the exact same form of the gravitational potential energy, which was G m1 m2 over R, the distance between their centers of mass. This is the exact same thing. R is still the distance between the centers of mass, but now the masses have been replaced by charges. So this is what I was talking about in an earlier video when I said one way to look at mass is as a gravitational charge. Okay, so now we have this constant K in this case. So we had a G before, and K is about 8.99 times 10 to the 9th. Okay, and then units, again, we know that this is going to have units of energy. And so over here we have units of charge squared over length. So we see that K is going to have units of joules times meters divided by Coulomb squared. So these are the units of this constant K. And remember, for G, we had something that was on the order of 10 to the minus 11. For K, we have something on the order of 10 to the 9th. So we see that the electric energy is much greater than gravitational energy. And one of the unsolved problems in physics today is trying to understand why. It's something called the hierarchy problem, is why electric and electromagnetic energy is so much greater than gravitational energy. But there's another big difference between electric energy and gravitational energy. So if we set up our axis of R and our potential energy, we see that if we have a case where Q1 times Q2 is less than 0, in other words, maybe we have a positive charge and a negative charge, or a negative charge and a positive charge, then in this case we get a 1 over R potential. So it looks exactly like the curve that we had for gravitational energy. But now, what if we look at the case where Q1 times Q2 is greater than 0? For example, if we have two positive charges or two negative charges. Well, in this case, notice this potential doesn't have a negative sign in front. So if the sign is the same, then we have a 1 over R potential. Okay, so it's the same exact formula, but now we have two different potentials depending on what the charges were. We didn't have that in the case of gravitational energy because we didn't have a negative mass. And one thing that occasionally there are people and groups that try to look for something that has a negative mass, because if you did that, then you could basically reverse the sign of gravity. And so you read about some of these science fiction stories about them having like anti-gravity. And that's what they're talking about. If they could find some way to find something that's a negative mass, then they could flip the sign of the energy, which would flip the direction of the force. And so, we'll work a couple problems with this, but when we're working problems now with electric potential energy, we work it exactly the same way we did with gravitational energy. We set up the problems in exactly the same way, only we're using a different formula for the potential.